Okay. Hello guys, welcome to the third lesson of DBA from Introduction to Practice. I'm your old friend Peng Wang, the global technical evangelist of OceanBase. After starting the first two lessons, I believe you have already gained a certain understanding of the core features of the OceanBase and its installation and deployment. Now this lesson will mainly introduce how to test the OceanBase. Let's get started. With the rapid deployment of our database industry, various database technology innovation and solutions has emerged. At the database level of our company, we usually consider various factors such as database performance, storage cost, and business scenarios. Usually, we use POC testing to examine the comprehensive capability of different data systems. So today, we will mainly introduce how to test our OceanBase from the perspective of user in the following four sections. First section, let's move on the first section, OceanBase test overview. In this section, we will mainly introduce the test points that can be focused on in our POC test based on the feature of OceanBase. The first thing I want to introduce to you is our database performance test. Performance testing is a key indicator in business selection and POC testing. It's also the focus of our sharing this time. The database divides the business into two classic scenarios, OLTP and OLAP. Enterprise generally use DTL to regularly transfer data from the OLTP database to the OLAP database. This approach brings two problems. One is delay, and the other is complexity. In the actual production process, various failures are often caused by the data synchronization delays or synchronization errors. In order to solve such problems, OceanBase provides the ability to implement HTTP, allowing us to support both OLTP and OLAP scenarios using a single dataset. In order to evaluate the performance of our database, there are several relatively recognized testing standards and tools in the database industry to evaluate the OLTP and OLAP capabilities of our database. In terms of OLTP, we often use standardized testing tools such as Sysbench and TPCC, which are mainly used to measure the database's ability to handle high-frequency transactions and online real-time transactions. On the other hand, to evaluate database OLAP performance, we usually use tools like TPCH to simulate complex queries and analytical operations, testing the system's ability to process and respond efficiently to large volume of data. In addition to the industry-recognized test standards models mentioned above, since OceanBase is highly competitive with traditional database in terms of syntax and functions, other testing tools are also applicable to OceanBase. For example, if we want to evaluate the comprehensive performance of the database in actual business scenarios, we can use GMAT to simulate the interaction between the user's actual business scenario and the database. This makes our test results more comprehensive and close to the real application scenario. Next comes our parallel import. In the OLAP scenario, parallel import of a large amount of data is usually involved, which is an indispensable part of the POC test. Customers are mainly concerned about the stability and speed of batch data write operations, which is crucial for user who needs to process a large amount of data migration or synchronization tasks. The parallel execution framework of OceanBase can also concurrently execute DML statements. For multi-node databases, it can realize concurrent writing of multiple motion and ensure data consistency. In addition, combined with the asynchronization dump, it can also greatly optimize our storage engine support for large transactions under tight memory conditions. As shown in this figure, our current kernel supports the following three main import methods. The first is load data, which is essentially implemented through the transaction method and method of batch insert. This is the import method that our OceanBase has supported since version 3. The advantage is that it's relatively stable and is also suitable for scenarios where the amount of imported data less than or slightly less larger than the memory. The second is our bypass import, which is a new export method added in version 4. This method skips the SQL transaction and the map table module and directly writes the data into our access table. Therefore, in scenarios with a large amount of data, the performance will be better, and it's suitable for scenarios with large amounts of data being imported. The third method is to load data locally. The limitation of the first two methods is that the data must be on the server, while the advantage of load data locally is that the data file can be placed anywhere that can connect to the server, which is more flexible. We can flexibly choose our import method according to our usage scenario. It's worth mentioning that all three methods support setting the parallelism of import. We can improve the efficiency of our import by setting the parallelism. After completing a parallel import of our business data compression is also a test point that our users often pay attention to. With the company's growing focus on cost management, effectively processing and storing massive amounts of data at a low cost has become a core competitive advantage of our database products. By conducting a data compression test, we can know a comparison of the storage space before and after data compression. And we can also evaluate whether compressed data has an impact on the query and transaction processing performance of our system. The OceanBase is based on a storage engine with a high compression ratio. It has developed a set of compression methods for mixed row and column encoding of the database, which we call encoding. Before the universal compression algorithm, we perform a compression encoding on our data. This will not affect the data reading and writing performance, but can also significantly improve the data compression rate and help our users greatly reduce storage cost. After the OceanBase version 4.3, column of storage is opened. It also brings further optimization space for our storage compression. Once performance and cost requirements are met, another critical concern is disaster recovery performance. High availability database systems in our application architecture plays a vital role in data storage and querying, especially in recovery scenarios. The high availability of enterprise data is crucial to ensuring business continuity, so our high availability test is also an important factor in our database performance assessment. OceanBase leverages the Paxos protocol to implement a multi-copy disaster recovery solution. In early versions, it achieved RPO is 0 and RTO less than 30 seconds, setting a new standard in database industry. And in OceanBase version 4, OceanBase further enhanced this by providing RPO is also 0 and at the same time RTO less than 8 seconds, making it the first database in the industry to reach an RTO less than 8 seconds. So high availability testing is also an important part of our evolution of our database product to ensuring the security and continuity of our data in abnormal scenarios. Next, I will introduce several factors that affect OceanBase's performance. Let's look at how our common benchmarks can achieve better performance in OceanBase. Database performance is often influenced by various factors. We can break down and analyze these factors from the inside out. First, on the hardware, we need to provide the best environment as much as possible. Hardware constraints generally set the upper limits of our performance, right? In practice, our hardware environment is often limited and fixed. Max the use of limited resource is a key focus for OceanBase performance optimization and improvement. Then let's look inside. The operating system serves a bridge between hardware and database software. When our hardware conditions are fixed, we need to reasonably allocate operating system parameters, including CPU, network, memory, I/O, disk I/O, and others, to ensure that our database software environment can max the use of hardware resources. When we have these operating environments and database software is deployed and running normally, the next thing we can do is do something tuning inside our database. First one, we need to make strategic resource allocations, such as defining zones, partition tables, and table groups, and adjusting replica distribution based on the actual business scenarios to minimize the unnecessary distribution overhead. Additionally, we can optimize the runtime performance of software by tuning database parameters and performing target maintenance operations, like merging and statistical data collection. This approach allows us to further maximize database performance without compromising system stability. Next, we will introduce each in detail. First, we ensure operating system parameters are optimized. When deploying clusters with OBD and OCP, we conduct a check to verify that our OS parameters are fully compatible with the OB server. For specific check items, please check the link. This includes checks on file system, kernel parameters, unlimited restriction, and essential environment dependency. Beyond these OS parameters that support OB servers' normal operation, we also provide additional configuration guidelines to improve resource scheduling and achieve optimal performance. It's mainly divided into three parts. There are network parameters, memory parameters, and AIO configurations. The network-related parameters are mainly used to optimize the performance of network connection and transmission in high concurrency scenarios. The memory-related parameters are mainly used to control the database to use memory as much as possible to process our data operations. The last one is to improve the performance and throughput of our database when the database is performing a large number of AIO operations. Of course, we only list some common parameters here. In actual process, we need to make some personalized adjustments based on the system configurations. We need to focus on the resource allocation and discuss it from several perspectives: software, hardware, and table resources. Let's talk about the first part, software and hardware resources. Typically, the hardware indicators we consider are CPU, memory, and disk. For CPU and memory, it's essential to allocate resources exclusively to the database as much as possible. Disk usage requires special attention, as the OB server writes three types of data files. There are system logs, transaction logs, and data files. Deploying this on a single disk can lead to bottlenecks due to resource contention. Therefore, when resource permit, we recommend to use three separate SSD disks. If only one disk is available, partitioning the logical volume or disk array is advisable. Two transaction log-related parameters are critical. The C-log recovery parameter, which defaults to 80%, and the C-log stop writing parameter set at 95%. When the C-log recovery threshold is exceeded, recovery will begin. If recovery is delayed beyond stop writing threshold, the node will cease writing. Enabling log flow limit function on the system log disk can help manage the disk I/O. Disk I/O bandwidth used by the system logs. However, this might lead to an error indicating that the log write limit has been reached, suggesting a need to increase this limit for better log analysis. To control log recovery, note that these parameters only take effect when this parameter configuration is set to a non-zero value, and both parameters must be used in tandem to work effectively. For tenant resources, OceanBase operations on a multi-tenant architecture requiring sufficient resources allocation for test tenant. Importantly, the state tenant should not be used for testing due to its limited resources. Test tenants should be established based on the remaining resource availability. Consideration for tenants' resources include CPU and memory, and log disk space, and IOPS. With the introduction of version 4, OceanBase now features log disk space isolation and IOPS isolation between tenants, which enhances overall system stability by providing one tenant's high writes load from impacting others. For distribution of primary zone, the distribution of replica is determined by setting the primary zone. In OceanBase, the leader replica handles transaction read and write requests in strong consistency scenarios. Therefore, the leader distribution across partitions significantly impact the traffic distribution. For a multi-node OceanBase cluster, setting the primary zone to random can efficiently distribution partition across different zone nodes, max resource utilization. Next, let's discuss resource allocation related to our tables. In OceanBase, we can partition tables into smaller, more manageable parts. This approach allows for separate management of data partitions, which means that when a partition is unavailable, the query optimizer automatically excludes it from the query plan, ensuring that queries remain unaffected. For resource-intensive DDL tasks, such as rebuilding indexes and tables, we can operate at the partition level instead of the entire table, providing great flexibility in management. In TP scenarios, partitions can help reduce shared resources usage, when in AP scenarios, they can expedite query processing. Additionally, OceanBase's storage and load balance units are partitions, enabling different partitions to reside on different nodes. This distribution promotes even data allocation across the cluster. For table groups, a table group is a collection of tables that enhance data organizations. By default, data from different tables is randomly distributed. However, by defining a table group, we can control the physical proximity of related tables, reducing distributed overhead and enhancing performance. In version 3, tables added to a table group needed to have the same partitions method, which imposed restrictions. Starting from OceanBase version 4.2, the partitioning concept has been removed, allowing tables with different partitioning methods to be added to a table group. The sharding attribute is categorized in two types. The first one is sharding equal 9. The table's partition are consolidated on the same machine without restriction on the partition types. Data from the tables in this group is scattered across multi machines, ensuring consistency in data distribution. The second one is partitioned. This requires all tables in the group to have consistency partition defines, allowing for partition-wide join. The last one for indexes. Indexes in OceanBase are categorized as local and global. Local indexes are for partition table, only reference data within their specific partition. Functioning similarly to indexes, for non-partitioned tables. In contrast, global indexes have an independent data distribution strategy and can operate in both partitioned and non-partitioned modes. We recommend using global indexes in two scenarios. The first scenario is when the business requires global indexes beyond the primary key. The second one is when the query doesn't include the partitioned key condition and the business table has lower concurrency rights, allowing us to build the global index based on the query conditions. Global indexes requires caution, as the write may trigger distributed transaction across machines, impacting performance under high concurrency. In contrast, local indexes are preferred when the queries align with partition boundaries, offering efficient partition pruning and balancing query and write performance. In summary, while global indexes have specific users, local indexes are generally recommended for the common users. Okay. Next, we will mainly introduce parameter tuning of the OceanBase version 4 in order to improve the user experience and overall capability of the database. We have done a lot of performance optimization work so that user can get better performance based on the basic performance tuning scenario. For the OLTP scenario, you can see that the OB server parameters mainly make some parameter adjustments for SQL and system daily information collection. This meaning of the parameter is also intuitive and clear. We can adjust them as needed. And there will be a more detailed introduction on the OceanBase official website. The parameters related to OB proxy are mainly to improve the performance and stability of the OB proxy in large traffic scenarios. Tuning of the compression protocol is to reduce the CPU usage of proxy. When the CPU is limited, we can make corresponding configurations to improve the overall performance of proxy. For the OLAP scenario, we mainly adjusted the default timeout of SQL execution and the max network packet size to limit this to hard conditions. In addition, we increased the memory ratio used for SQL calculation so that data calculation can be performed in memory as much as possible. Finally, a node can allocate multiple node threads for parallel execution, dividing a SQL query into subtasks that can run across multiple processors to enhance overall performance efficiently. After understanding the parameter tuning, let's look at two important maintenance operations. Compaction and statistical information collection are two relatively important maintenance operations in OceanBase, also play an important role in performance. The compaction will merge the SS table and mem table of the current major version with the full static data of the previous major version to generate new full data. OceanBase will perform two layers of compression on data during the compaction. The fourth layer is based on the encoding compression of the database internal semantics. The second layer is based on a compression algorithm specified by the user, using some common algorithms specified by our user to perform another compression, not only save storage but also greatly improve our query performance. More importantly, based on the storage architecture of OceanBase, compression has basically no effect on the write performance, right? The second is our statistical information collection. In OceanBase, the optimizer will try to generate an optimal execution plan for each input cycle. And generating an execution plan often requires effective statistical information and a row count estimate. Statistical information refers to the statistic of the optimize. It's a data set that describes the tables and columns in the database. It's a very critical part of selecting execution plan in the cost mode. In OceanBase Optimizer, statistics are stored in the internal table as normal data, and a cache of statistics is maintained locally to improve the optimizer performance. It's worth nothing that since version 4 of OceanBase, statistical collection is no longer completed in daily compaction. The above are two important operations in our database. We will also perform our compaction and statistical information collection in our TPCC and TPCH tests. Next, we will introduce the common used benchmark tools and how to tuning them. First, let's talk about Sysbench, the most commonly used tool in OLTP testing. Sysbench is a scalable, multi-thread benchmark tool based on LunaJet that can perform performance tests on aspects such as CPU, memory, and database. It's often used to evaluate the database load under different system parameters. You can modify the source code of Sysbench. You only need to customize some Lua scripts to implement tests of different database types. One of its features is that its table structure is relatively simple, mainly including 4 fields, and the data type is relatively simple, including our int and char types. The right figure shows the 9 SQL statements of our Sysbench, including point select, range query, sum range query, sort range query, and others. You can see that all operations are single table operations without complex table join queries. In addition, some of the scripts we often use actually combine the SQLs mentioned above, such as our OLTP read-only script, which actually includes all selected queries, and our OLTP read-write scripts, which actually includes our read and write operations. The performance indicators including TPS, QPS, and RT. RT means response time. Sysbench is a commonly used tool, so we will not introduce it further here. Another important OLTP performance testing is TPCC. TPCC is a benchmark test for OLTP launched by our Transaction Processing Performance Committee. Since its release in 1992, TPCC has become one of the standard of OceanBase of database transaction processing capabilities. TPCC simulates our commutative sales model. TPCC contains 9 tables, as shown in the upper right chart. Looking at the chart in the lower right center, TPCC contains 5 types of transactions, namely new order, payment, order status, delivery, and the stock level. They occupy different properties in TPCC test. What needs to pay attention to is our new order transaction because our TPCC model use TPMC to measure the max effective throughput of our system. The transaction test is based on new order, measuring our measure performance by the number of new orders processed per minute. Now, let's look at the model design for using TPCC and OceanBase. All tables except item holding significant data, so we will partition them accordingly. Since all tables related to WID column, we will use table group to reduce distributed transactions and enhance performance. To further optimize query efficiency and avoid global index performance issues, we will create local indexes on customer and order tables. For more details, you can refer to the instruction on the OceanBase official website. Next, we will introduce our commonly used OLAP test model TPCH. TPCH is a test set data developed by our TPC organization to simulate a decision support application. It simulates a transaction between suppliers and customers. TPCH implements a data warehouse based on the database three paradigms and mainly simulates 8 basic relationships. TPCH includes 22 complex queries, covering statistical analysis and multi-table joins, complex conditions, as well as group by and order by operations. The evaluation criteria are mainly of each query. The overall data model of TPCH is a typical snowflake model with a total of 8 tables. Here we also briefly talk about the table structure designed by TPCH in OceanBase. The first one is except the nation table and the region table, the rest of the tables are partition tables. 2. According to the association the relationship of our query, 2 table groups will be established for the order table and the line item table, as well as the part table and the part supply table to improve performance. We will flexible set the resource distribution of the table according to the actual business scenario to improve our overall performance. Next, we will introduce how to perform the 3 tests mentioned about the OceanBase. On the OceanBase official website, there are relatively detailed test steps for the 3 test tools mentioned above. The official website introduces 2 testing methods. One is the traditional manual method, where each step is done manually. The other is OBD method, which automates the entire test process for one-click testing. Here, we will focus on the OBD method, covering practical tips and usage examples. The three commands below are one-click tests for different scenarios. The deploy name is the name of an OBD cluster, and the tenant name corresponding to the tenant. Please note here, system tenants typically has limited resources, so avoid using the system tenant for testing. For the TPCC test, warehouse indicates the number of warehouses, which affects the data volume. Load workers set the concurrent data loading threads. Terminal sets the concurrent testing requests, and run minutes specifies the test duration. Adjust these parameters based on your machine's capability. For the first test, we use lower values to complete a full run-through, then increase as needed. In 𝘕𝘂𝘁 testing, this parameter specifies the OB server directory _AS and indicates data scales consistent with this parameter in 𝘕𝘂𝑐C. Additionally, useful operation includes 1. -v for detailed test output. Without it, only basic information is shown on the screen. And the second one is -o for tuning. This parameter is used for tuning. The value can be 0, 1, and 2. 0 means no tuning at all, and 1 means only basically tuning parameters, and 2 for full tuning, including parameters that requires a restart. For 𝘕𝘂𝘁 testing, you will often see this DT. First parameter is DT. DT means disables local TBL transfers to the remote TBL directory. And the second one is test only. Test only means skip initialization and runs only the test cycle. Okay. Next, we will give two examples. The first one is a test case for 𝘕𝘂𝘁. At the top is the test command. We can see that the name of the tested cluster is perform. The name of the tenant is also perform, and the username is root. Then we will transfer the data file to the data 𝘕𝘂𝘁 directory of our OBD server. And the amount of data we tested is 1, which means 1G. From the figure, you can see that the test command points out the entire test process. The second test case shows the -v parameter we just mentioned. Since there are many logs after adding -v parameter, we will give two examples. The first example is screenshot the data we generated. After adding -v, you can see that OBD will generate 10 test data based on 𝘕𝘂𝘁 native tools. The second picture shows the login information of the tuning parameters. OBD will first check the parameter value of the current system. If it's different from the recommended parameter value, it will be changed to the recommended value during the test. After the test is completed, OBD will also help us restore the parameter's value to the initial value through the recovery step. Next, let's look at the troubleshooting ideas when the problems occur during the benchmark test. Let's first look at the OLTP scenario. First one, we recommend using OB_DIG to do the status check on our OceanBase. OceanBase is a native distributed database. So the analysis of its fault causes involves many factors, such as machine environment, configuration parameters, and operating loads, and others. So troubleshooting requires collecting a lot of information. OB_DIG can help us efficiently collect and analyze fault information of faulty nodes. The official website has a more detailed introduction and download link. So we will not introduce here. You can go and try it. Let's go back to our analysis of OLTP scenario problems. The first one is troubleshooting. Set the primary to a single zone, run the OLTP point select case in sysbench, and observe if the OB server CPU is fully utilized and to simplify the scenario. 2. Lower CPU usage. If the OB server's CPU usage is low, check for bottlenecks. Accesses CPU, memory, network boundaries, disk I/O, and latencies for each components, as any bottleneck could limit OBS performance. The third one, test steps consistency, ensuring test steps match the official guidelines. The first one, common issues in small-scale testing. In small-scale tests, dedicated systems resources are recommended. Limited hardware resources may cause QPS drops. Use the top command to monitor the OB server's process. Focus on mini-merge and mini-exe thread usage. Next, let's look at the performance problems analysis in the OLAP scenarios. First, we still recommend to use OB-Diag to check the status of our OceanBase. Then, further troubleshooting the problem. The first one is check tenant resources configurations. Evaluate whether the tenant CPU and memory configuration is sufficient based on the amount of data related to the test. The second one is observe the CPU water level and disk I/O load of the machine under parallel execution. The third one, check whether the test steps are consistent with the official website standard steps and the KOB server's parameters configuration in OLAP scenarios. For examples, this parameter, for the example, you can see that here we have two parameters. The first one, by querying the this parameter, whether the status field is idle, you can determine whether the merge task is completed normally. The fifth one, check this parameter to see if the status field is success to determine whether statistic collection is proceeding normally. The last one is check whether the execution plan is normal. Focus on the DLP value in the execution plan and determine whether the SQL query is executed in parallel normally. Okay, in the previous chapters, we mainly introduced the influencing factors and testing method of OceanBase performance tuning, as well as some troubleshooting ideas for common problems. In the last chapter, we mainly introduced some other test scenarios and corresponding method. First, let's look at the parallel import test. We can use the custom table in the TPCH test as a basis and create an empty table custom tool with the same table structure, and performing in the operations with PDML tuning off and on to observe the effects. Below are three steps. The first one is set this parameters, adjust the max SQL execution time to prevent the transaction from timing out due to excessive size. The second one, without parallelization, observing the execution results, we can see that without parallelization, it takes OceanBase about 110 seconds to insert 15 million rows of the data in a single transaction. The third, after clearing the customer tool, start PDML and execute the insert again. Generally speaking, if there are no multi-SQL statements executed concurrently, the parallelism of a single SQL statement can be set to the number of tenant CPUs. It can be seen that after PDML is enabled, the time taken by OceanBase to insert 15 million rows of data into the same table is reduced to about 17.3 seconds. The performance improvement brought by the PDML features is about 6.3 times. The feature can help users in scenarios where batch data processing is required. Next, let's move our focus to another point, which is our data compression test. OceanBase is based on the LSM-tree architecture and has developed its own storage engine. The data is divided into two parts: baseline data and incremental data. The baseline data is stored on disk, when the incremental data is generally stored in the memory. This enables data to be stored more compactly on disk, with baseline data undergoing fewer updates. This approach allows for additional compression of the baseline data, enhancing the database's overall compression ratio without impacting query or write performance. Next, we will introduce how OceanBase imports a large amount of external data and how to observe the data compression ratio. Based on the line item table in the TPCH test, the total data size of line item table before data import is 75 G. Below are three steps. The first step is, after the import is complete, execute the command to manually trigger the merge. The purpose of this step is to merge the baseline data and the incremental data. The next step is to query the OceanBase table. When the status in the table is idle, it means the merge is complete. The last step is to use the following query statement in the sys tenant to view the storage usage of data after importing to OceanBase. For example, here, we query in the space usage of the leader replica for the line item table. It can be seen that the total data size of the line item table before importing is 75 G, and the compressed data size is 22.15 G. The actual data space required is 23.11 G, and the compression ratio is about 3.2. Finally, we have high availability test. The high availability of our cluster is also one of the product highlights of our distribution database architecture. RTO is an important indicator for measuring high availability, and in the OceanBase version 4, RTO has been controlled within 8 seconds. The first step is deploy a 3-node cluster. Set the primary zone is Z1 and connect sysbench directly to Z2 or Z3 OB server. Stress test command example is here. You can see it. Here we need to pay attention to that these parameters: MySQL ignore error number. We added this parameter error number that MySQL client will prevent our client from disconnecting after receiving this error number. The second step is this this command to use this kill command to observe the service recovery time. From this picture, we can see that the stable TPS value is about 500, and it dropped from 21 seconds to 27 seconds. The process token about 7 seconds, which means the RTO less than 8 seconds to restore the service. Okay, now let's review the key point of this lesson. The first one is high performance HTTP capabilities. The second one is parallel import and data processing. The third one is data compression. The last one is high availability testing. Okay, do you still remember how many compression methods we used in OceanBase? Do you remember? Or you forget? Okay. If you have any questions, now is the perfect time to ask. Okay, no questions? Before we wrap up, I'd like to remind you that our next lesson will be next Thursday evening, where we will be covering the OceanBase migration and synchronization. We look forward to see you there. You can also reach out anytime through our OceanBase Discord or GitHub community for further assistance. We are always here to help. We will be sharing how you can access the course materials and today's presentation slides in the comments section of this video. All the resources are free. Don't forget to subscribe to our OceanBase YouTube channel and join our community to stay up to date and get involved with us. See you guys. Bye bye.